It's my great pleasure to introduce Phil Rash, who's visiting us today from PNNL in Eastern Washington. A few words about Phil. He got his got two bachelor degrees from the University of Washington in 1976, one in atmospheric science and one in chemistry, and then went to Florida State to get his master's in meteorology, and also a PhD from Florida State, but he spent that time at NCAR when he got his PhD, and stayed at NCAR afterwards as a postdoc and a scientist for about 20 years, I think. Is that right? Yeah. And then moved to PNNL in 2008, and he's been there since. And Phil works on a range of different topics in atmospheric science, general circulation, atmospheric chemistry, and most recently has done a lot of work on geoengineering, and is also in charge of that chapter, geoengineering chapter, in the upcoming IPCC report. So we'll hear about some of his work on geoengineering today.
Thanks, Trudy. It's a pleasure to be here, and I'm sorry for the delay in getting started this morning. It's fun to be here, and I've enjoyed chatting with some of you this morning as well. I'm going to talk to you about geoengineering, which has, over the last 5 years or so, occupied more of my time than I ever planned it to. I started out working on it at the invitation of Paul Crutzen, who wanted somebody to work with him on modeling a particular geoengineering problem, and then gradually got more and more entrained in it over the years. The work that I've done has mostly been through cooperation with some postdocs and young scientists, and I'd like to tell you about some of that work today. When Trudy and I talked as well, she mentioned to me that there was going to be a series of 4 talks on geoengineering in the seminar series, and that, but Alan Roebuck who I gather was also one of the people asked to give a presentation, chose to talk about nuclear winter. So what I've decided to do is to provide you with an introduction to geoengineering, as well as then tell you something about my own personal research and what I've done in it. And I like to start off with this cartoon. I almost always, sorry guys, everything that could go wrong will go wrong. Let's just turn it off. I like to start off with this cartoon because it sort of tells you what the difficulty is. I hope all of you have had a chance to read it. The issue is that we're gradually recognizing that fossil fuels are an issue in climate change, and it's very difficult to make the transition to other sources of energy. And another example of that I like to show is this picture from a paper by Raupak in the Proceedings in the National Academy, in which he shows in the black lines here a time series of the fossil fuel emissions as estimated from measurements, alongside a set of scenarios that have been used historically for anticipating the changes in fossil fuel use, and are also used to project out fossil fuel changes to as far as 2100. Now, these particular scenarios have now been superseded by a different set, but in the early days it doesn't make a whole lot of difference through 2010 or so. You'll notice that in the recent past, post-2000, that the emissions have exceeded the highest levels that were anticipated by this set of scenarios. These are actually just the scenario averages, and there are fans of scenarios associated with each of these lines that do exceed the current emissions, but these are the midpoints or the best estimates of those scenarios. And if you look at what's happened in the more recent past, you can see that the problem is just getting worse in spite of our attempts to deal with with fossil fuel emissions. So this has sort of motivated the possibility of considering something called geoengineering, which I define here as being an intentional change to the climate system, which is designed to counter some of the effects of increasing greenhouse gases. And I've introduced a question here to recognizing first that we are changing the climate system and whether it's worthwhile thinking about introducing changes deliberately rather than carelessly. And this is sort of provocative. I don't really, I'm quite uncomfortable with answering this with the answer yes. I don't want to, but it's, there are some reasons why it might be interesting, as I will leave you with a message in my closing, that there might be some reasons to consider deliberately and very temporarily introducing changes as a mechanism for understanding the physics of the atmosphere or the climate system better, even if one made the decision never to deploy any of the strategies which I'll talk to you about today. So the other thing is to acknowledge the people who I've been working with, and they're listed either down below, they're a little less directly involved with my current research, and the ones up above who I'm going to cite a lot of the work that they've been doing with me over the last couple of years. So to begin this, I want to remind you about the energy flows in the atmosphere and what's regulating the temperature of the planet. It's essentially the planet is initially governed by the amount of sunlight entering the top of the atmosphere. Some of it is reflected off of clouds, molecules, and aerosols in the atmosphere and returns directly to space. A lot of it, and some is absorbed as well as the sunlight passes through the atmosphere. Some of it is again reflected at the surface, and about half that entering the top of the atmosphere is absorbed by the surface. The temperature of the planet warms and begins re-emitting in the infrared, and some of the energy is returned to, or begins its traverse back to space in the form of infrared radiance or radiation, and other parts of it appear in latent and sensible heat fluxes. As the energy is emitted from the surface, it's again absorbed, this time in the infrared, and quite a bit of it is emitted or is absorbed and re-emitted by the atmosphere. Some of it goes up and the rest of it comes back down. And a good part of it is taken up by greenhouse gases, and clouds also act as a greenhouse medium, if you will. So the mechanisms that are being I'm going to talk to you in quite a bit of detail about one class of geoengineering techniques, which is called it was with tongue-in-cheek originally labeled as solar radiation management, or SRM, but it also is called sunlight reflection methods. These are methods which are methods that are designed to increase the reflectivity of the planet slightly by either increasing the brightness of clouds or introducing additional aerosols into the atmosphere or changing the surface reflectivity of the atmosphere. Some of them are also designed to decrease the greenhouse effect, either by removing greenhouse gases or by making high-level clouds, cirrus clouds, less opaque to infrared energy. And Trude's worked in that area very recently. So this is that's a very brief overview of the basic concept of geoengineering, and I'm going to spend another 5 or so slides on kind of putting a little bit more detail into this and talk to you about results from the early research that I did, primarily in using one of these sunlight reflection methods, which utilizes stratospheric aerosols as an analog for volcanic eruptions, and another way of changing boundary layer clouds. And I'll spend quite a bit of time then telling you about some very general results of a model intercomparison activity that's been taking place over the last couple of years. And you'll see that there are some names that I've repeated or indicated in an earlier slide there also. So I'll get into more detail about GeoMIP later. So there are these two different classes of methods, which I've already described to you, the carbon dioxide removal and solar radiation management. Here are a variety of the techniques that are being postulated that could work. And if you begin to look at these in some detail, then what you find is that they can be broken down into sort of two broad classes of results. The carbon dioxide removal mechanisms are, because they're getting at the heart of the problem, the increase in greenhouse gases, by removing the carbon dioxide from the atmosphere and sequestering it in some non-gaseous form, if you could do it safely, that would be getting at the heart of the problem. It might be a possible long-term solution. All the estimates that have been put together right now are that it would be very slow. If you were to use natural methods, it could take hundreds of years to draw down the CO2 that we've already injected in the atmosphere in the last 50 years, and it would be quite expensive. And then there are a class of techniques, these SRM techniques, which I'm characterizing as probably not a long-term solution, but they're very cheap to do. Even if you take the costs that have been estimated for some of these strategies and multiply it by orders of magnitude, it would still be cheap compared to either making a transition from a fossil fuel-based economy or to employing some of the carbon dioxide removal techniques. So there was a nice report that was written by the Royal Society about 3 years ago now, in 2009, and I've taken a cartoon from that which attempted to do an assessment of the costs, the effectiveness, whether it's a variant of a natural phenomena, how hard it would be to get it ready, and they've scored each of the various strategies which I've mentioned to you before in terms of these things, and two that have been deemed relatively promising are listed here in the upper right corner of this figure: stratospheric aerosols, which I'll talk to you more about in a minute, and the boundary layer cloud seeding. But in fact, if one was ever to consider doing this, it may actually pay to consider a combination of approaches. By far the most satisfactory solution is to just cut the fossil fuel emissions from the start. But also you could do this in concert with sucking out CO2 and changing the reflectivity of the planet for certain reasons, and we can talk about that later also. By the way, I really like to be interrupted when I give talks, so if people have questions, feel free to inject them in it. So the first thing that I wanted to do is just to remind you, this was actually the eruption of Pinatubo a couple of days. This is a pre-eruption of Pinatubo. The day after that, it really went off. And what one sees in the observations is that following that eruption, which took place in '91, the planet cooled by about 1/2 degree, as indicated by the solid black line here. The models which have introduced the aerosols are able to reproduce this kind of cooling as well. And there were other consequences to the planet also. One is able to find changes, easily measurable changes in the amount of water vapor, for example, the column integrated water vapor. And models also reproduce those signatures. There are, in addition to cooling the planet, there are some negative or, some consequences that are of some concern. The top panel here is showing you, these are both from Trenberth and Dye's paper, and is showing you a time series of the amount of sunlight and long-wave energy reaching the surface and the sum of those two. And the sign convention is such as to, when you see this positive change by 5 to 10 watts per meter squared, this is a reduction in the sunlight reaching the surface. And at the same time, if you monitor the amount of freshwater discharge from rivers across the planet and then estimate from it the land precipitation, you can, the conclusion is that there is a significant reduction in the amount of precipitation reaching the surface at the same time. And I'm going to come back to this in more and more detail because it's one of the, well, really that has been the focus of some of the recent research that I've been doing with my postdocs. So for those of you who don't know how stratospheric aerosols work, I've taken this cartoon. There are many sulfur-bearing species that are emitted by volcanoes, either the small volcanoes that percolate along all the time, as well as emissions from various ecosystems that introduce sulfur-bearing gases in a reduced form. They're relatively inert, and many of them become well mixed, and when they reach high altitudes, those gases can be oxidized. Well, some of them are inert, some of them are very reactive, but a significant amount of the sulfur species reach the stratosphere, the lower stratosphere, where they're oxidized to make sulfuric acid gas, and the temperatures in this part of the planet, this is from the equator to pole here, are sufficiently cold that the sulfuric acid gas condenses and makes small particles. And while you think of volcanoes as putting a lot of ash into the atmosphere, it's not the ash that's really the thing which affects the cooling of the planet. It's the particles that form afterwards from the sulfur-bearing species. These sulfuric acid particles they're mixtures of sulfuric acid, nitrogen species, and water. They mix along this layer of the atmosphere called the tropopause, just above it, and gradually they get mixed in to the lower part of the atmosphere, where clouds scavenge them very efficiently, and they can also, the particles can get quite big and they sediment out as well. If the particles are mixed into higher altitudes, the temperatures actually get warmer again, and those particles evaporate, and they undergo chemical reactions which put them back to sulfur dioxide, and then this cycle can return over and over again also. So I'm going to talk to you now about a set of simulations and the conclusions that we've come from them using general circulation models and some very high resolution models called large eddy simulation models as well. And at least for the general circulation model studies, what I'm going to tend to do is to show you differences between a series of simulations. Oftentimes I'll call it a control simulation, where we assume that CO2 concentrations exist in pre-industrial concentrations, and there is no geoengineering done. And then we will difference them with simulations in which we increase CO2, and we oftentimes increase it to double or quadruple the amount that is present in the times around 1850 at 285 parts per million, or even present day. It doesn't really matter much. And look at the differences between these two simulations, and then to also explore what might happen if we introduce various geoengineering solutions or combine increasing CO2 concentrations with geoengineering. And we look at differences in various important fields and the processes which are controlling them, and try to infer from this what would happen if these techniques were to be employed in the real world. So just to give you kind of a feel for how things operate, what I'm showing you here are a set of simulations that were done with the general circulation model that I use, the CCSM. And these are this top panel is a cross-section of the atmosphere of the planet from the South Pole to the North Pole, and altitude on the ordinate here in kilometers. And what I'm showing you here is where the aerosols are located from introducing a source of sulfur-bearing species, in this case sulfur dioxide, which is introduced at about 25 kilometers in the tropics. That sulfur dioxide oxidizes and makes these aerosol particles, and they spread out and occupy this region of the planet. If you integrate the mass of this layer of aerosol species in the model and plot the vertical integral, the mass-weighted integral of these species, you get a picture that looks like this, with the red values showing where the aerosol would tend to collect, and the yellow values telling you where the aerosols would be relatively low. I've chosen to show you the June, July, August distribution because I want to make the point that when the sun is shining in the northern hemisphere, that the radiative reforcing, or the reflectivity, the reduction in the amount of sunlight reaching the surface, maximizes over the North Pole, where the sunshine is and where this layer of aerosol is also. And that there's also a signature of the aerosol in the tropics, where we have been emitting the precursor gases. That oxidation takes place over a few days to a month in time. And so you also see a reduction in the sunlight reaching the surface in the tropical regions. So what are the consequences of this? In the top left panel, I'm showing you the surface temperature change, the difference between an experiment and the control. In this case, for a doubling of CO2, and the temperature change is indicated here on the right. The left panel is for the doubling of CO2, so you see the warmest temperatures in the polar regions, and really the warmest temperatures are at the winter pole. And and then on the right panel, I'm showing you the consequences of introducing these sulfuric acid particles into the lower stratosphere. This is for a simulation in which I haven't attempted to entirely balance the greenhouse gas warming, but you can nevertheless see that the temperature changes are much lower than they would be in a world in which there was no geoengineering. The middle panels here are showing you the impact on precipitation. The blue values are indicating where precipitation is reduced, and the red values where it's increased. And what you see is a signature which is common to many general circulation models of an increase in precipitation in the tropical regions for high CO2 concentrations, and a decrease in the flanks of the tropics here as well. And then where the colors are white in all of these panels, it's an indication of areas where there's not much change compared to the pre-industrial simulations. The changes are small. And where you see these hatch marks is where the differences are statistically significant, according to estimates that I can describe to you in more detail if you're interested. But I'm also showing you that in the lower panels, a similar calculation, a simulation that was done with a different general circulation model. And the take-home message here that you'll see is that the signatures are quite different. I think you should only pay attention to the right panel. Can't remember what the exact strategy that we used for the left panel is. But the point is that where it's low, where there are increases and decreases in this model is not the same as where there's increases and decreases in this model. And so the regional consequences of this geoengineering are quite uncertain at this moment. But that's one message, and the other message is just that the changes, the GCMs are hinting that the changes in precipitation would be reduced compared to a simulation in which only greenhouse gases were allowed to increase. There will be other consequences to the planet as well. It ends up that ozone depletion takes place on these stratospheric aerosols, and there are sites for the reactive photochemistry that's involved with ozone depletion, particularly in the presence of the reactive chlorine species that are produced by the release of chlorofluorocarbons. And what I'm showing you here are changes in the concentration of ozone that are as calculated by a model that we put together to try and assess what the consequences of the would be to the photochemistry of the atmosphere. And what you see here is in blue regions, there's ozone depletion, and in the orangey colored regions, there's actually an increase in ozone. And if you calculate again the vertical integral of this latitude height cross section, then you would conclude that in general, the introduction of the so the stratospheric aerosols would decrease ozone in the, over Antarctica and would actually prolong the presence of the ozone hole by 30 to 50 years. This ozone hole is supposed to go away as CFCs gradually are depleted from the atmosphere around the end of the century. So it would take a process that's going to go for at least another 100 years if our models are correct, out another 30 to 50 years. There would actually be some increase in ozone in the tropical regions. So another strategy is to brighten clouds. I mentioned this to you as well. And I've chosen to start by demonstrating the impact that humans can have on clouds by showing you these features in the cloud fields. This is a satellite retrieval. In this case, I think this is off the coast of California. And these streaks here are so-called ship tracks, which are caused by the emission of pollution into the boundary layer. And those small particles act as sites where cloud drops form. And if you increase the number of sites, cloud condensation nuclei in the boundary layer, then what you find is that those particles are competing for the available water vapor. And so you will get each droplet that forms would be a little bit smaller than it would be if the pollution was not introduced into the atmosphere. There would be more drops and they would be smaller than the areas where these ship tracks are not seen. And I also want to show you that these signatures occur in a variety of different cloud types. There are here a variety of different kinds of clouds, ranging from what are called closed cellular convection to open cellular convection. And you see these kind of brightening effects in both areas. So simple theory that was developed by Sean Toomey in the 70s suggests that if you introduce more aerosols, they make more drops, smaller drops, and by simple physics you can show this would produce a more reflective cloud. And estimates have been made of how much it would take to change or to change the clouds in a manner which might counteract. Clouds are a very effective mechanism for cooling the planet. And Tony Slingo, in a paper in 1990, suggested that by relatively modest changes in the number of drops, and changes in the cloud drop size, or increases in the oceanic cloud cover, you could counteract the CO2 doubling. And these numbers that I'm providing you with here are the numbers for any one of these effects to operate. If all of these effects are operating, then the changes would be much more modest than this in each of these features. So this stimulated an idea by John Latham in the 90s, which was to maybe consider deliberately introducing particles into the boundary layer. His idea was that you take some seawater, convert it to very small drops, introduce these seawater drops near the ocean surface where they'll evaporate and make salt particles, or salt and organic aerosol particles that would act as very efficient cloud condensation nuclei, and to produce the aerosol particles in a manner which would let them be very efficient cloud condensation nuclei that would outcompete the natural aerosols in making cloud drops. So Latham suggested that this was an idea which could be used as well for brightening the planet. And a variety of people have made studies about what cloud systems would be most effective to brighten. And this diagram, which I'm not going to talk to you about in very much detail, indicates some of those regions. Where it's yellow and red, these would be effective places to brighten the planet. And these are areas where these marine stratocumulus and trade cumulus systems reside. So what happens if you introduce those, if you assume for the moment that we could introduce and control the behavior of the clouds perfectly, what would those clouds in those regions that I just showed you, what would be the impact on the precipitation distribution? In the top panel here, I'm showing you the distribution from a general circulation model that result that I made. And in the lower panel, the change from the geoengineering. So what it indicates is that there are places on the planet where precipitation would be reduced, where it's very intense here in the intertropical convergence zone, and there would be shifts of the South Pacific convergence zone as well. Now, this again is another model. This one is a model run in England, and I want you only to focus on one particular location, and that's over the Amazon. In this model, in this simulation that I did, the model is showing that precipitation would actually decrease over the Amazon if you introduced these aerosol particles. In the Met Office model, it shows that you would, did I say decrease? I meant increase, and in the Met Office model, the aerosols would decrease precipitation. So again, the signatures are very uncertain here. There's also effects on sea ice, and in spite of the fact that we're introducing these changes to the clouds in the tropics, you can show that just because there's generally a reduction in the amount of energy reaching the surface of the planet, you can have an impact on the sea ice distributions. These blue areas are showing you the, okay, so this is the southern and northern hemisphere where the changes are in late summer for each of the hemispheres in March and September. For a doubling of CO2, the blue areas are indicating where the sea ice, the model predicts the sea ice would be lost. If you put just the right amount of geoengineering in, then you reduce the effect significantly. If you put in a whole lot of geoengineering, then you will potentially overdo the effect also. So I've told you that these effects operate on the clouds, but what it's important to recognize is that clouds are very poorly handled in general circulation models today. And so we've also attempted to do a much more careful job of simulating those clouds and to do it in a large eddy simulation mode over a very small region of the planet for a very short period of time. And I'm going to focus on this region off the coast of California where these clouds are very prevalent and show you a set of simulations done with approximately 1 million times smaller grid spacing than the mesh that you see here, which is typical of the kind of a mesh that is used for solving, for doing climate simulations over the globe. So what we're going to do is to focus on simulations. These are satellite simulations, again, which show over very narrow regions. This red box is indicating the size of one of the general circulation model boxes. And inside that red box, you can see areas that are have what are called open cellular convection, as indicated in the top right panel, as well as closed cellular convection. So what we've done then now is to mimic introducing a ship, or a set of ships in this case. This laser pointer is run out of juice. And what the ships do is they sail from the left-hand part of this model domain, which is only about 100 kilometers long and 100 kilometers high. These 3 ships are sailing from left to right. And when they're doubly periodic dimensions, so when they go out one end, they return and come back in the other side. And I'm showing you snapshots at 6 hours, 12 hours, and 18 hours into this simulation. And the right panels here are showing you the particle the distribution of seawater particles that we're introducing into the model domain. And the left panel is showing you the changes in the clouds. So the clouds start out to be mixtures of closed cellular convection and some open cellular convection. By this time, the ships have propagated most of the way across the domain, and you can see the impact of the wakes. And 6 hours later, the clouds have evolved, and in this region, the albedo is relatively low, and they're low. The clouds are, the seen albedo is also quite low, but you can still see remnants of the the plume of aerosols that were introduced into the model, as well as some areas where the closed cellular convection is also maintained. And, but you'll also see that there are these wakes of dark regions here, which are to each side of the cloud systems or the cloud plumes. And this is a feature which is shown later in time as well. We've looked at various seeding strategies with these detailed high-resolution models, and I'm showing you here what would happen if we were to introduce one ship that's injecting the same mass of seawater into the atmosphere, but doing it just as one ship and going over and over through the model domain. And here's the signatures that you see if we use this different seeding strategy. Again, what you see are bright regions surrounded by darker regions. So one can compare the albedo of these clouds to the albedo that would be present in the simulations without having introduced the extra clouds. And the conclusion is the ships do brighten the planet, but they don't brighten it anywhere near as effectively as are hypothesized in GCMs right now. The distribution of sprayers, the magnitude of the flux, the kind of cloud systems, the environment, they all make a huge difference in terms of how much the clouds will brighten, and the GCMs are not doing a very good job of mimicking these effects right now. So I'm going to now switch gears and kind of, that was my introduction, and just remind you that the models and the observations have suggested that the global precipitation distributions would drop if the planet became brighter, and I'll spend some time talking to you about why, and then the models are frequently disagreeing on regional responses. And this geomip intercomparison activity, this model intercomparison activity, was designed to try to reduce some of the variations in the simulations that were done by the investigators who've looked at geoengineering up to now. And what we've chosen to do is to try and set the problem up so that everybody can do exactly the same simulations.
Well, if you're going to leave the sea spray for a second, maybe I'll ask a question.
Okay. Yeah, I am.
If you have like a small island or an atoll in the middle of the ocean where waves are crashing into the beach and producing a big spray of salt particles, wouldn't it do the same? So can you observe this in the current atmosphere, this process going on of localized regions of intense wave breaking causing...
You can't see it. You can't see it in they haven't been able to because clouds have so much variability. They haven't been able to demonstrate it in from seawater or sea spray. There's a related study which has been done, which is there is a small volcano near one of the Hawaiian Islands that's going off right now, and one can very clearly find the wake of the volcanic plume, which it's a low-level volcano that just goes steadily downstream of the volcano. So you can see it perturbing trade cumuli brightness. But for seawater, I'm not aware of any studies which have shown that. So this just tells you how the geomip intercomparison activity goes. So what one does is with the black line, I'm indicating that a simulation is done with pre-industrial forcing up to a particular point in time, and then a perturbation is introduced. And in one perturbation, you quadruple CO2, indicated by the red line, producing a positive forcing, and the planet is expected to warm. And in another simulation, you introduce a negative forcing, which is just sufficient to counteract what would be present in the 4 times CO2 experiment. And the simplest possible thing to do is to turn down the amplitude of the sun. And this is quite far-fetched, obviously, but there is a strategy which I haven't spent any time mentioning, but was on the previous slides, which is to introduce reflectors in space, which could scatter some of the sunlight that would normally, you would put it near a Lagrange point, and it would be just sufficient to scatter just enough sunlight back to space to counteract a particular amount of warming. Now, it ends up that those reflectors in space, the estimates are, it would be enormously expensive, and we don't have the technology to do it today, so it's not looked at very often, but it would be a very close analog to this particular experiment. And then finally, you do experiments in which you turn both the positive and the negative forcing on simultaneously. And I'm going to now kind of switch to showing you some results from this intercomparison activity and framing it in terms of fast and slow climate responses. And for fast experiments or fast responses, the typical way that people characterize what they call the fast response to the climate system is how are fields changing before surface temperature really has had a chance to respond, or to respond very strongly. And the slow responses is what happens to the fields after the surface temperature has been allowed to change. So I'm just going to review the mechanism that's been developing from a variety of people in some later slides here. But the first thing I'll do is to show you the results of the quadrupling of CO2 in the northern hemisphere winter and summer. And for the 4 times CO2, the experiment was designed to really hit the planet with a hammer, and there's a very large warming of 7 or 8 degrees with temperatures as high as 16-degree changes in the northern hemisphere poles to the quadrupling of CO2. And then the results for the combined forcing, so cooling the planet by reducing the amount of sunlight reaching the surface, and warming the planet by introducing the 4 times CO2. And what you can see are that there are still some residual effects. You see a high latitude response primarily in the winter hemisphere polar region, and also some other regions where there are some discernible differences. And the stippling in these plots is been introduced to indicate where 75% of the dozen models that participate in the model intercomparison agree as to the sign of the difference. So wherever you see it stippled, it's an indication that there's a coherent signature across all the models. So now I'm going to just try and go over what happens with these changes in the forcing agents. And I'm going to first go over what would happen if you cranked up the sunlight. And if you do, then increasing the amount of sunlight would increase the surface flux. You would get a warming, but a very small warming, but enough to change the stability, to increase surface turbulence, and through the turbulence to be moving more both heat and water out of the boundary layer, and anticipate that you would get an increase in precipitation. And with a slow response, after the temperature begins, after this positive forcing begins to be felt by the system, you would get a warming in these. I should have said that these are supposed to be just schematic diagrams of temperature versus altitude for a particular column or for the global average of the planet. The temperature changes would kick in, and then following that, you would also see water vapor and lapse rate feedbacks kick in, but we don't typically, we try to isolate the water vapor, the feedbacks from the other fast and slow responses. How about for CO2? Well, the first thing that would happen is increasing the greenhouse gases would immediately warm the column aloft because of the absorption and emission of the outgoing long-wave radiation, and the fact that the greenhouse gases are relatively long-lived and the heating is relatively uniform over the column. And what it does is to stabilize the column and reduce the amount of turbulence near the surface, leaving the surface a little bit warmer and a little moister than it would otherwise be, suppressing precipitation. So in a fixed SST experiment, if you just double CO2, the precipitation actually goes down. But of course, if you allow the surface temperature to respond, then the surface temperature eventually increases. And at that point in the game, the evaporation rates can also increase. And you will you get more moisture in the column, and combinations of lapse rate feedbacks, water vapor feedbacks, and the just absorption and emission by the increased water vapor as well as the CO2, which is what we think is really happening to the planet. So now, what happens if CO2 is high and sunlight is reduced? So the red line is supposed to indicate the profile from the high CO2. And if you were to decrease the sunlight, then you will again increase the stabilization or the stability of the profile, and again reduce evaporation compared to the present day. And if you put just enough in to bring the surface temperature back to the present day or pre-industrial temperatures, then you're going to be left with a column which is more stable than it would otherwise be, even if the surface temperature is the same as today. So it's precisely that last situation which we think is the explanation for the reduction in precipitation that is seen in the trend following a volcanic eruption, as well as the signatures that we see in the models also. I think I'm going to skip this figure. So here I'm showing you the changes from the GeoMIP experiment for a 4 times CO2 precipitation change on the left. And in this case, the signatures are quite similar to the things I showed you before, with an increase in the intertropical convergence zone. Now this is the multi-model mean from the 12 models that were in the GeoMIP intercomparison, and a reduction in precipitation along the flanks of the ITCZ, as well as significant increases elsewhere on the planet, including increases over places where there are monsoons and increases to high latitudes as well, and in the storm tracts. After putting in the geoengineering, you get a very different signature. In this case, consistent with the volcanic signatures, you see a reduction in the precipitation over a lot of places on the planet. But again, I'll point out to you that the white regions are regions where the precipitation changes are relatively modest. There are some significant regions where the models agree that there would be changes, either reductions in precipitation or increases in precipitation. If you look at the components of this thing, then the top panel is showing you it's the same as the figure I showed you on the previous panel. Here's the signatures in the evaporative flux, and you see that really there are vast areas of the oceans where there are differences, but there are also very significant changes over over some of the land masses, and the combination of precipitation minus evaporation is shown here. If you look as well at the primary productivity, indicating the effect that it could have on ecosystems, you can see that primary productivity for the 4 times CO2 minus control increases. Let's just ignore the middle panel, and the lowest panel here is the geoengineered world. So this would be the productivity of a world with today's or pre-industrial temperatures, but with an enhanced CO2 concentration. It just is suggesting that plants would have an easier time of it. So now I'm going to just describe to you briefly some of the changes in precipitation intensity. Over the top panel, I'm showing you, so that on the abscissa here are the precipitation intensity for the models, showing you whisker diagrams, which are not showing up very well, I apologize, but for different precip intensities, and this is the yeah, the difference, the change in precipitation compared to the control for the ensemble of models for 4 times CO2 for the ensemble of these 12 models and for the geoengineered experiment on the right. And what you see, so these are only monthly mean precipitation. This is not the daily or instantaneous precipitation differences in the frequency of occurrence. But you see that in a 4 times CO2 world, that the high precipitation amounts will tend to increase when measured globally or when measured only over the monsoon regions, both over land and ocean, land in red and blue oceans, as well as in the intertropical convergence zone. And that if you then begin to try and tease out what's going on in the geoengineered planet, you see the precipitation is reducing. The frequency of occurrence of high precipitation indices is actually reducing over all regions of the planet. So this would indicate that the most intense precipitation would tend to be the ones which are most strongly influenced. The same occurs in mid-latitudes, but it's even more dramatic for the models. The precipitation intensity in mid-latitudes goes up a lot for the 4 times CO2, much less for the geoengineered planet. And the top panels are for the winter precipitation, and the lower panels are for the summer in the northern hemisphere. We've also looked at the signatures for these various monsoon regions, and the signatures are essentially the same. Trudy, I'm not paying attention to the time, but how am I doing at this point?
Time to wrap up.
Okay, good. I can do that pretty quickly. So here's the take-home messages. The first one is, this diagram is intended to show you a measure of the difference compared to present-day climate compared to CO2, and when for various fields, which are indicated here, when these symbols are located near this top line, it indicates that this is the change in the climate as a function of the amount of geoengineering. And when the symbols are located near this location of 0 here, it's indicating that this particular amount of geoengineering was enough to return, in this case, northern hemisphere sea ice to something that looks like present-day amounts. But you'll see that that amount of geoengineering might return northern hemisphere sea ice, but it wouldn't return surface temperature precisely to present day. It wouldn't return southern hemisphere sea ice or precipitation. However, if you measure according to, I think I'll just skip this one. The messages are quite similar. Now here's maybe the last science result I'll show you. Alan Roebuck did a nice study a while ago in which he made a simulation of the transient evolution of the planet to a 1% per year increase in CO2. And then at a certain point, he began geoengineering. And the different colored lines here show different amounts of geoengineering. The red line being designed to take you back to pre-industrial surface temperatures. And the blue line indicating very little geoengineering. And he fixed it for at a particular solar amount of sunlight reduction for this period of time, for about 40 years or something. And then postulated, well, what would happen if for some reason we decided that a mistake had been made and we needed to turn off geoengineering? And you see these temperature traces showing the consequent recovery of the planet when you turn off the geoengineering. The rate of temperature increase is very rapid, and this would really seriously stress ecosystems, for example, or adaptation by humans as well.
After, looks like 2005, when the geoengineering starts, are we continuing to put CO2 in
Yes,
the atmosphere?
we are. Yeah. So this red line, this thick red line, shows what happens to the temperature if no geoengineering takes place. So it continues to go up. And the blue line, or black, or this sort of orangey colored line is for various amounts of geoengineering. So if just a little geoengineering, the planet cools a little bit, but it still goes up. It stays cooler than it would have been. The black line the same, and the red line, he's introduced a lot of geoengineering, so you don't see the response yet. I think I'll skip this one. And I'm going to close now. Just there's lots of messages. This was sort of an overview as well as a few recent results. There's lots of messages to communicate to you, and lots of subtleties I can't talk to you, or I haven't had the chance to talk to you about. But these are some of the things that I wanted to leave you with. The first is there's an inexact compensation by sunlight reduction methods. It's not really a complete solution. You can see that you can't balance precipitation. If you try to balance temperature, you won't balance the amount of sea ice. To invoke this kind of a geoengineering strategy is at best a partial solution. And some issues are not addressed at all. For example, ocean acidification. In any of these strategies of modifying the amount of sunlight reaching the surface, the ocean will continue to take up CO2 and it continue to acidify. Because of the inexact compensation, it doesn't make any sense to me to start unless there would be a clear path to an energy transition to a non-fossil fuel burning solution, and you knew how to mitigate the CO2 effect. So if you wanted to get past, or to avoid, for example, the possibility of exceeding a 2-degree temperature change to reduce the probability of reaching a tipping point, maybe it would make sense to invoke some kind of a SRM technique, but only if you really, because it gets increasingly risky as CO2 increases, it would be a risky solution unless you knew there was a way out, and a risk-benefit analysis would be necessary. Because it doesn't compensate everything equally, there would be winners and losers. There's obviously a huge number of ethical, moral, and practical issues, not to mention the issues of diplomacy and negotiating treaties to do this kind of stuff. And then the last thing that I want to just say is, one of the things which I have suggested in a number of papers is that there might be useful things that could be learned about the physical system by deliberately introducing small-scale effects into a set of clouds, for example, that wouldn't really affect climate, but would tell you whether we really understand how clouds brighten, for example, or what the consequences of that brightening would be to the surface energy balance. These are things which are just basic physics, and they're relevant to geoengineering also. And they could be invoked even if one, from the beginning, ruled out a full-scale deployment that was designed to counteract CO2 increases. And I'll close here. Thanks.
Questions for Phil?
Any relationship in these studies reflecting on drought areas that need more precipitation due to agriculture?
Yeah, there are implications in some of the figures that I showed, which I didn't spend time on, but if you look, for example, in the monsoon regions, you see that there are, with 4 times CO2, you get many situations where there are reductions in the frequency of occurrence of these intensities, and there are other circumstances where you see an increase in the frequency of occurrence of these very intense precipitation situations. So there will be, the implication here is that there may be times where droughts and floods are being affected by the perturbations that the anthropogenic perturbations that we're introducing. And GCMs are tending to say that it's they call it sometimes the rich get richer phenomena, but that wet areas are going to get wetter and dry areas are going to get drier. And I think the signatures that the GCMs are providing is to say those situations will occur much less frequently if you invoke geoengineering. Now, I don't know whether to believe the GCMs or not. but they're providing a consistent signal of those things. And I've already told you that that the climate models tend to not agree very well in terms of their regional characterization also.
That's the very point I wanted to ask about. The AR4 report had a lot of consistency between models on the global predictions, but not so much on the regional.
Yeah.
And my friends tell me that the AR5 report is about the same.
Yeah.
In other words, they haven't really added much confidence to the regional report. So I wonder if you could, I think this bears some relation to what you're trying to do here, and I'm trying to figure out what's the reason why we're not making progress on the regional predictions, and to what extent does that impact what you're trying to say here?
Well, I don't know the reason why we're not making better progress on regional characterizations of climate change right now. I know there are many aspects of models with many easily identifiable deficiencies. We're working on them. But the thing is that also I see as a model developer is that over the last 5 years, we've spent a lot of time putting in new physics, putting in carbon-nitrogen cycles, for example, putting in isotopes, putting in a variety of different new things. Aerosol cloud interactions are treated much more comprehensively than they were 6 years ago when the previous generation of the IPCC was in. But we haven't tried, so what we've been doing is making models more complex and not necessarily trying to hammer down the systematic errors. We have done that also, but I don't think we've been doing as much of it as it deserves. And I don't know where, I don't know how to, I can't identify an optimal strategy for where we ought to be putting our energy, because who's to say that the additional complexity that we've worked on over the last 5 years is not necessary to get the regional effects right. So I don't know where, I can't reprioritize the research and say what is most important right now.
You made a point that when you use the LES model, that it wasn't getting close to what the changes were coming from the GCMs. What sort of orders of magnitude?
Right. Well, so one of the messages is that the detailed models also suggest that it's possible to brighten clouds. The whole scene is brighter than it would be in the absence of geoengineering. Introducing the sea spray aerosols does cause the scene to brighten, but not as much as GCMs brighten. And this is a signature that I think GCM modelers, we know, and Trudy can tell you too, is models we think they're overly sensitive to the introduction of aerosol. GCM models are.
One final question.
So, a lot of modeling results, but aside from your last point in the summary slide, where are the experiments?
Yeah, well, part of the problem is it's such a controversial topic that a number of us, there are white papers around proposing field experiments, and there is work that has been done that to, for example, produce sea spray with the right size distributions to affect the aerosols. But to do a sort of a comprehensive field experiment, let's say a field experiment that affected a domain over a few hundred kilometers on a side, with a significant amount of change in the albedo, to do a 1-month experiment would be tens of millions of dollars. And we've floated the white paper around to program managers, and it's just too controversial to be considered at this point in the game. Now, 2 years ago now, Lynn Russell at UCSD, Scripps, went out and released a bunch of smoke and aerosol particles off the Scripps Pier, off the coast of California, and looked to see whether she could find ship tracks, for example, and to see whether it could be one could predict the behavior of those ship tracks? And the answer is, it was a very, she bought the smoke generating machines off of eBay for a few $1,000s. She had a small NSF grant to do this. She mentioned in one paper that it was applicable to geoengineering, but it was not a geoengineering experiment, it was a cloud seeding experiment. The clouds which are being seeded here, by the way, are ones which are quite different from the cloud seeding that's being done to promote rain, for example, and I could talk to you about that if you wanted to know. But at any rate, there's no funding to do this kind of work right now.